Hello everyone, welcome to PHY 211 test for review. I just want to say that the test has a lot of conservation of test 4 has a lot of conservation of energy. That's going to be big in this test. Let's first talk about rotational kinetic energy, which is really basically a function of omega, the angular velocity. And so we're going to do the simplest case. Simple case of mass, and it's going to rotate about this axis in a circle. Here's our radius. Okay, so linearly, we know k as a function of v is equal to 1/2 mv squared. That's linear or translational. But rotationally, we can say since v equals r omega, we can say 1/2 v squared is r omega squared, so r squared omega squared. And if you notice, right here is an I, a moment of inertia. So I for this particle is equal to mr squared. And now we have our rotational kinetic energy. Let's erase that I. We'll put it here. There. Okay. Oh boy. Okay, did a little erasing. All right, so let's carry on here. So let's talk about this for a little bit. This right here is our mass, quote unquote mass, for rotational motion. It's the desire to stay still, to keep from rotating. Okay, well, when we're dealing with linear stuff, linearly, we have mass, and the mass total is equal to the sum of all the masses from 1 to n. So that's just mass 1 plus mass 2 plus mass 3 plus blah, 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 up to mass n. Okay, so that's your mass total. Well, the same thing goes rotationally. We have our I total. And in this case that I just described, our I total is that mr squared. So this is I total. I total would be the sum of the masses. We only had one mass times their radius squared. So we say I to n mi/ri squared, where ri is the distance from the axis to the point, to the center of mass of the mass that we're dealing with. And of course, that just equals I1 plus I2 plus IN. Okay, so far so good. Let's do more on a moment of inertia. We talked about it in class. You need to know that if we're going to calculate a moment of inertia, the most general way to calculate it is to do this integral over the entire system. So that is true. And I told you that I wouldn't expect you to do it. That is just something that you need to know. But what I did say is you'll need to know the parallel axis theorem. So what is the parallel axis theorem? And I gave an example in class. I'm going to do the example again, only I'm going to do it very quickly. So the parallel axis theorem says the I for a parallel axis, I'm going to call it axis 2, is equal to the center of mass plus the mass of the object times the distance from the new axis to the center of mass squared. So we used a thin rod. And we had a center of mass rotating about it. And the I for it at the center of mass is, what is it? 1/12. And of course, the whole rod is L, length L. So we have our 1/12 ml squared. And if we put our new axis, so here's axis 1, here's axis 2. The center of mass is here. So the distance d from axis 2 to the center of mass is equal to L over 2. If we square d, then we get L squared over 4. And now we can write I axis 2 is equal to 1/12 ml squared plus our mass times L squared over 4. And that comes out to be 1/3 ml squared. So, and if you verify that, you can verify that in the book with the table where all the axes are. And the moments of inertia is what I really want to say. The moments of inertia are all found in the book. You'll notice that for a thin rod at this axis here, this is what you get. So the parallel axis theorem works, and you'll want to know how to do it. Let's move on to torque. So torque. Torque has a lot of ways that we can write about it. Torque equals, the net torque equals I alpha. But we also have that an individual torque is equal to R cross F. And depending on the nature of them, if R is perpendicular to F, then the torque is equal to RF. But it's not always equal to RF. It's not always perpendicular. So when it's not, it's RF sine of theta, which is the angle between them. So when R is not perpendicular to F. So that, what does that look like? That would look like, here's our circle, here's our force, here's the radius, and here is the angle between them. If you lay it out so that they are perpendicular, it turns out that the equivalent radius is r sine theta, and the equivalent force is F sine theta. So you can do it two different ways. You can say that the torque in this way is equal to F times R sine theta. And you could do it this way and say that it equals to R times F sine theta. Just like that. Okay, what about the direction? Let's write another, oh boy. Let's write another one. We'll draw another one. Here's our thing. Here's the force coming off. What about the direction? So here's our R. There's F. So if the torque equals R cross F, then we put our fingers along R and we curl them to F. And the only way to do that is for our thumb. So here's the right hand rule. Our thumb points down. If you do this, hold your hand up to R. Here's R. Hold your hand up, put your fingers along R, and then curl them towards F. So when you curl them towards F, you have your thumb points into the page. And sure enough, that is the direction for the torque. I don't know, let's just do this one. We'll apply some torque this way instead. And here's our radius. So you do it this way, you put your fingers along the radius R and you curve them toward the F, and you get that your thumb points out of the page. Okay, so right hand rule. Good. Next. Power rotationally. So P is power. Is always your work divided by time. So always, which means that power is equal to d work divided by time, d time. And rotationally, we know that our work is equal to the torque times theta. We talked about that, we derived it, and now we can say that the power is equal to d work over d time, and so that means that it's tau d theta dt, as long as your torque is constant. Which we will consider it constant all the time, the whole time. For you, it's constant. So this ends up being your angular velocity. So we can say that the power is equal to our torque times our angular velocity. Okay, so then we started talking about equilibrium. Equilibrium is all about whether it's static or not. There's some things to keep in mind here. Is it static or not? Okay, so there are two conditions for equilibrium. One, the first condition, which is the linear condition, which we always used since we started learning about forces, and that is that the sum of the forces is equal to our I don't like that A. A of the center of mass, that is equal to 0, which means since mass can't be 0, that means that ACM must be equal to 0. And then rotational is the second. That means the sum of the torques, which is I alpha, equals 0. I cannot be 0 for a massive object. If it's an object, it's massive. So its moments of inertia has to be non-zero, and we get that alpha must equal 0. So those are our two equations for static. What does it mean, though, for all of that? We have these equal to 0. All that means is omega is either 0 or it's a constant. That's it. And the same goes here. V equals 0 or V equals a constant. So you don't typically think of something being static means that omega equals 0 or a constant rotationally, and linearly. So even though these things might be actually moving with respect to us, it doesn't matter. It's still considered equilibrium. Simply because these things are true right here. Okay. I hope nobody has questions on that. Our next thing. I kind of want to talk about something being in equilibrium versus not equilibrium. So the easiest thing to do is to draw another stick. We'll put a fulcrum on it. We'll apply some forces. I'm just applying rando forces. So here we go. And then this one is at a radius 3 from the pivot point. Here's our pivot point. This one is radius 2. This one would be radius 1. Those are our pivot points, and we can do a sum of the torques. So we'll do one first. They're all perpendicular to each other, so we don't need the angle between them, so we can just say this, R2F2 plus R3F3. And that whole thing is going to equal I alpha. All right, so here's our fulcrum. And if there's actually something here, if it's not equal to 0, because all of these could end up equaling 0, if you define your coordinates to be, let's say, negative this way and positive that way, then R1, F1 is negative. Which ones are positive? F3. So R3, F3 minus R2, F2. Wrong. That one's positive, this one's negative. And we're also subtracting off R1, F1. So the only one that's positive is R2, F2. If this one is different, how do I want to say this? This whole thing could equal 0. I alpha equals 0 means that F2, R2 is equal to R1, F1 plus R3, F3. So we would know that. If that's the case, then that implies this is equal to 0, and then we're static. Okay, but it might not. So I alpha could be not equal to 0, and then that implies we have a net torque that's not equal to 0. And the net torque then is, oh boy, something we have to deal with, or we will have as an answer, or whatever. It'll be a part of our situation. However, if these do equal each other, if this is true, then that means that alpha is equal to 0. When that is true, all of a sudden you don't have to keep your pivot point the same. Pivot point can change. And you can make it arbitrarily anything you want. So we can say, let's say we don't know anything about F2 or R2. Well, we'd have to know something about R2. But we don't know anything about F2. we can change and make our pivot point here in a static situation. So this is our new pivot point 2. So if we move about pivot point 2, then we just need to know the difference between R3 and R2. And we can then do our sum of the torques is equal to F3R3, where this is R32, the difference between R3 and R2, that's negative, and we're going to make F1 also negative. F1 R1 2. So R1 2 is this distance. And this is R3 2. And this would be our I alpha equals 0. Because we didn't know anything about that. This was a question mark. Now we can figure out some things. Maybe we didn't know this one, and we can figure that out. And we do, and then we can go back and change our pivot point back to pivot point 1 at the fulcrum. Why doesn't this one show up in our sum of the torques? Because F2 times 0 equals 0, because we've placed the fulcrum at 0. So R22 is equal to 0. So that's why it doesn't show up. Okay. In our sum of the torques. All right. So let's move on to angular momentum. Angular momentum is pretty big on this test. Angular momentum is called L. It's equal to I omega. Just like linearly, momentum is equal to PMV. Here's our mass, here's our angular velocity, here's our mass, here's our linear velocity. We already talked about just now the two conditions for equilibrium, and since omega in equilibrium must be 0 or a constant, if L is not going to be equal to 0, that means that omega is equal to a constant. So L is equal to L, let's say L final. No. Let's do delta L equals, if omega is a constant, delta L equals 0. That implies that. What does that mean? That implies that the final is equal to the initial. Right. But we all know, and we did a lab just now, or recently, that means L final could equal I final, because the I could change. So we have I final, I omega, our initial could be I initial omega initial. And if those are equal, we've conserved angular momentum. So that needs to be alpha equals to 0. So the net torque equals 0 in this case. And I'm going to continue to talk about angular momentum here for a little bit. Delta L, if we take and do the calculus of this whole thing, we can get delta L is essentially dl. And if we use the impulse formula, I better put a dt on the time. That's delta L equals torque times dt. So really, delta L dt, let's move this up a little bit. Delta L dt is equal to our torque. And of course, it's all vectors. So angular momentum you can come up with it by doing the integral those two integrals. And so that's one way of getting it. L is also equal to your radius cross your momentum, which is this momentum right here. And let's see, what else do we have? So this one works. This one works. And do we have one more? Nope. But if delta L over delta, or dl dt is equal to 0, then we are conserving angular momentum. And we're back up to this. Okay, next topic. I've got angular momentum all over town. Okay, we did do the can rolling down the hill. So we had I think I can do this. I'm going to do a ruler and see what happens. All right. Okay. We did this thing with a can. And we rolled it down a hill. And we got to, from this height down to that height, and we wanted to know what the V final was. Our V initial was 0. And we did this neat thing where we used the conservation of energy. And we wrote out that the energy initial was equal to, since there's no rolling, and all we had was mgh for energy. Our final energy will be equal to the kinetic energy rotationally plus the kinetic energy linearly, and we can write that out. V squared, and we did all of that work to input what a cylinder I is. We took that from that one sheet, the one table in the book. So it's 1/2 the mass of the cylinder times the radius of the cylinder squared about this axis down the center. So, great. If we take this I cylinder and we put it in right there, then we are going to be left with 1/2 times 1/2 mr squared omega squared. But this piece, if you note V equals R omega, that equals V squared. So we're given, we multiply those two together, we get 1/4 mv squared plus 1/2 mv squared. A fourth plus a half is 3/4 mv squared. So that's our E final, and that equals our E initial. So these two guys have to be equal. And then we can solve that for our V final. I better put little finals in here. And that ended up giving us that the V final was equal to 4/3 GH square root. Okay, I'm telling you that because you'll want to be able to do this on the test. So you just might have a different moment of inertia for a different object. Okay. So that's good to know. That takes us through all of the angular momentum stuff. I want to do one other thing. In space, angular momentum is conserved really well because friction is very low. So, not a lot of friction means that if you have an Earth-Moon system where the moon is going around the Earth, that will go on for billions of years. So, and hardly any change, delta L will be very small. So yes, delta L is hardly ever conserved, but if you look at the small enough time, if t is small, then delta L is conserved. In space, because friction is very low. So, in space. So please keep that in mind. That's why it works so well. So what is the force we're dealing with in space? The force in space is gravity. Gravity. Gravity kills. No. Okay. What about gravity? So we have Newton's universal law of gravitation. Which says that F12 is equal to mass 1, mass 2 over r, the distance between them, times g in the direction, oh, whoops, there we go, and that equals minus F21. Put some of these guys on it. We've got our hat direction, and there you go. So this is the universal law of gravity. Why is it universal? That's because everyday objects around in your life and astronomical objects all use this equation. So both big and small, it works for. So it is universal. Okay. And being universal, the gravitational constant is also universal, and that gravitational constant is 6.67 times 10 to the minus 11 newtons, because we want newtons, and we have to divide out meters squared per kilogram squared. So here's our kilogram squared, here's our, so they get divided out. So that's our units on G. Okay. This will be needed. And now we can talk about gravity near Earth's surface. So the force of gravity is equal to the mass of whatever object we want times the mass of the Earth times g over the radius of the Earth squared. And in the end, using Newton's laws, that ends up being mg on the surface of the Earth, which is where we're talking. And what does that mean? That means that g is equal to mass of the Earth times universal gravitational constant times the radius of the Earth divided by the radius of the Earth squared. That is at the Earth's surface. And don't go thinking, oh, well, that's all there is to it, because any planet or object we can turn into our m. So this can be m. We can apply g to it and divide out by the radius of whatever that object is, how far away we are from it. And we can get that g as a function of r is equal to this for any object. And let me do a little erasing right here. That would be in the r hat direction. So we have a vector. Any object that works for. Okay, so objects have densities, and if we know that the density of the massive object divided by its volume, we're going to consider all objects to be a constant density. So rho average is equal to rho. And that, if we go through all the motions and we want to look on the inside, so here's our planet. We want to know what the gravitation is at this radius, r in, where this is the total radius of the planet or object. So we want to know what r in is. So on the inside, we did all the work of substituting in rho, and we came up with, on the inside, g is equal to 4/3 rho pi r in times g in the r hat direction. So this GR is linear in R. So we can say GR is linearly proportional. Linearly proportional to R. Let's keep this here so you can see it for a little bit. We then went on to look therefore, again, using conservation of energy, we went on to find out what the escape velocity is. From an object. So v escape from some massive object m. And we did that ke initial plus our potential energy initial equals ke final plus pe final. 1/2 mv squared minus mmg over r naught, 1/2 mv final squared minus mmg over r final. This equation is a big one for the test, and to find the escape velocity, here's our massive object, and we're going to be over here at RF, where RF is equal to infinity. So RF equals infinity, that means this whole thing equals 0. And when you're in a situation where you're super far away from this planet, it's all potential energy. So if it's all potential energy, then V final equals 0, because there's no kinetic energy anymore. So V final equals 0, and our potential energy at infinity compared to this planet is 0. So that leaves us with these two things equaling each other. So our escape velocity is then, these guys cancel, and we're left with a bunch of stuff. 2mg over r naught square root. Okay. One last bit. We have orbits. That didn't turn out good. Orbits. We saw, or we showed, that the velocity of an orbit is equal to the mass of the object you're circling over r, and the square root of it. So here's the massive object, here's our little guy, and he's got an omega, which means there's a velocity linearly, and of course we know that v equals omega r. So we can then find out, since this is true, we can do this. So that is true. And since we also know that the period of rotation is equal to 2 pi over omega, then our t for an orbit is equal to 2 pi, and then we just do the inverse of that. And that is our period. Oh boy. I can do this. What do we do here? Oh, I just want to go back. I just want to go back. Oh, yay. Okay, good. There we go. The period of our orbit is that. And so we covered a lot of things. And we are talking about angular momentums is what leads us into gravity. So this whole test really is, even though you think, oh man, this is totally two different things, and it kind of is in a way, but the force of gravity is the force that we are applying, applied force, in a perpendicular way. So that force of gravity is definitely perpendicular to the velocity. And that whole thing then leads us to our, we want omega. I omega, and I is equal to the object circling times its omega squared, or times the radius squared. Okay, so it's all summed up. That is concluding our review. Review concluded. End of review. VIEW.